Hey, what's up guys? Mr. Klinkerman. We are here trying to learn a new chapter. We finally got through our chapter about differentiation. And what we're going to do now is we're going to move on from that chapter about differentiation, which was part of a branch of calculus called differential calculus, and we're going to start learning what is called integral calculus. Now, I think that you're going to enjoy the integral calculus quite a lot. Hopefully you enjoyed the differential calculus. One of the things that's great about calculus is it is one of the most useful branches of mathematics. You actually get to see some places where the math you're going to learning is applicable. All right, no different here with the integral math or calculus. Now, in particular, in section 9.1, you can see that we're going to start learning about something called antiderivatives and what are called indefinite integrals, which actually those are two different words that mean the same thing. An antiderivative is an indefinite integral. All right, but we'll get to that here in a little bit. We are going to learn three things within this section in a few different videos. We're first going to start off in this video with learning how to find an antiderivative. So you're going to learn what an antiderivative is, and you're going to be able to find the antiderivative of a power function. We won't call it an indefinite integral yet, but again, they are the same thing. All right, and then in the next video, you're going to learn properties for finding indefinite integrals. And in the third video from this section, you're going to learn how to find a particular solution. All right, that means something specific when I say particular solution. You're going to learn how to find a particular solution of an indefinite integral if you're given what's called a boundary condition. Okay, so let's move on and see how you find out what an antiderivative is. Now, just based on that name, antiderivative, you might have a good idea of what an antiderivative is. And we're going to get to that. Hopefully, I'll be confirming what you've already suspected in terms of what that means. All right. We just talked about how in Chapter 7 you learned how to find the derivative of a function. And so everything within this little chart that I just put on the screen, you know how to find the derivative of. You know how to use the power rule, for instance, to find the derivative of 9x squared and get 18x. You know how to use the chain rule to find the derivative of the natural log of 3x plus 1 and get 3 over 3x plus 1. All right, you can confirm that. If you need to pause and make sure that's right, go ahead, but it is right. And then you would know how to use the chain rule again to find the derivative of that function in the last row to get this complicated looking derivative, but again, it's just a chain rule, pretty simple. Okay, well, I said you might have an idea of what an antiderivative is. And doesn't it make sense that an antiderivative is kind of the opposite of a derivative? All right, and that's exactly the case here. An antiderivative is the opposite of a derivative. Just like when you started learning addition, you then learned the opposite of addition, called subtraction. And when you learn multiplication, you learned the opposite of multiplication, division. Now that you've learned differentiation, you're going to learn antidifferentiation, which is its opposite. And as such, this shouldn't come as much of a shock to you. If I take the values in the second column of that table right there, it turns out that the antiderivatives for each of those would be the functions that we differentiated to get them. Okay? The antiderivative of 18x is 9x squared because the derivative of 9x squared gives you 18x. The antiderivative of 3 over 3x plus 1 is the natural log of 3x plus 1 because the derivative of natural log of 3x plus 1 gives you 3 over 3x plus 1. All right, same thing is true. This is the derivative of this because when you it's the antiderivative of this because when you differentiate 1/2 e to the x to the 5th power, this is what you get. All right, hopefully that makes a little bit of sense. Antiderivatives, the opposite of derivatives. Ignore that little caption right there. All right, but not this one at the top that's telling you when a function is called an antiderivative. All right, a function f is called an antiderivative of a lowercase f if f prime of x equals f of x. Okay, now I'm going to need to give you a specific example of what that's saying. Let's suppose that I looked at the function lowercase f of x equals 5x to the fourth power. And I wanted to know what is the antiderivative of that function. Well, I would have to think about what function would I take the derivative of that would give me 5x to the fourth power. And this is what it would be. Capital F of x is equal to x to the fifth power. And what we're saying here, well, let's just do a little confirmation. If you take x to the fifth power and you differentiate, all right, move the 5 in front, decrease the exponent by 1, you would get 5x to the fourth power. So we're saying that this function is the antiderivative of the lowercase function f, because when you take the derivative of the capital F, it gives you lowercase f. All right? Now, I do want to point this out. There's a very key term that you would miss out on if I didn't explain it to you. When it says that a function capital F is called an antiderivative of lowercase f, it has that word and, not the, it has the word and. Because it turns out there are a whole lot of different functions that you could differentiate that would give you 5x to the fourth. Now, I wrote down one example. Certainly the derivative of x to the fifth is 5x to the fourth, but so too is the derivative of x to the fifth minus 3, or x to the fifth plus e. Okay? Because remember that the derivative of a constant is always equal to 0. So it's impossible to say exactly what the antiderivative of a function is, but you can figure out that it's something plus or minus a constant value. All right, hopefully that makes a little bit of sense. Let's move on to that investigation from page 292 that my little caption is telling you to look at. And here is that investigation. And what it's trying to do is to get you into the mindset. What is it that you have to do in order to find the antiderivative of some function? Now, within this investigation, the first thing it's telling you to do is to copy and complete the table below. And it tells you the first entry is completed for you, and we need to take a careful look at that first entry right there. It says that the antiderivative of x is 1/2 x squared plus c. Now, if you think about the way that you find a derivative, this should make sense. When you find the derivative of 1/2 x squared, you'll do 2 times 1/2 is 1, and then you would decrease that exponent to 1, so you'd have 1x to the first power, which is just x, correct? All right. And then this plus c, well, that c is just a constant. Could have been plus 39,000, it could have been 0, who knows? Could have been anything. But you always put a plus c when you're trying to say what an antiderivative of a function is. All right, so the way I want you to think about this is we're undoing what you would do when you differentiate. When you differentiate, you multiply the function by its exponent and then decrease the exponent by 1. Well, when we're anti-differentiating, what you're going to be doing is you're going to be increasing the exponent by 1, and then you have to figure out something to multiply by, and I'm going to see if you can figure that out on your own. I'm going to give you one more example with this x squared, and then I'll see if you can do that. All right, if I'm trying to find the antiderivative of x squared, well, we know that it's going to have an x cubed. So let's go ahead and write that. But if you take the derivative of x cubed, it gives you 3x squared, not x squared. So we need to figure out how can we make this be just how can we make it so that the derivative of this expression is just x squared instead of 3x squared? Well, how about let's put a 1/3 right there, because 1/3 times 3 would be 1, and then you decrease that exponent and you get 2. The derivative of 1/3 x cubed is x squared. And we could have added any constant we wanted to at the end, and that still would have been true. Go ahead and figure out what the antiderivative of x cubed and the antiderivative of x to the fourth is, or what they each are. Now you can take a look at what I wrote down and see if you got the same thing, and hopefully you did. And you ought to notice a pattern pretty readily. And the pattern that I'm referring to is what is the relationship between the exponent of the antiderivative and the coefficient that you multiplied it by. And hopefully you notice then that it's the reciprocal. You always multiply by the reciprocal of whatever the new exponent is. So where you had 1/2 x squared, well, here you had 1/3 x cubed, those are reciprocals. 1/4 x to the fourth, 1/5 x to the fifth. And of course the way you determined what that exponent would be is by increasing the exponent of the original function by 1. Alright, and then just take the derivative of this exponent to get your coefficient. Okay, now if that makes sense, the next thing I want you to try to do is number 2. I want you to write a general expression or rule for the antiderivatives of x to the nth power. In other words, tell me what the antiderivative of x to the nth power would be, using that pattern that you just followed. Let's see what you came up with. What we just said is that when you're trying to find an antiderivative, you begin by increasing the exponent of your power function by 1. So for x to the nth, if we increase that exponent by 1, we get x to the n plus first power. And then we just multiply the coefficient by the reciprocal of whatever that new exponent is. The reciprocal of n plus 1 is 1 over n plus 1. And just because we don't know what constant could have been part of the antiderivative, we just put plus c to say that you could add any constant to that in order to get that antiderivative. Alright, hopefully you got that right. If not, hopefully it makes sense to you. Increase the exponent by 1, multiply the coefficient by the reciprocal of that exponent. Alright, now we can skip number 3. You can do it on your own, but I'm not going to discuss it right here. But I would like you to think for a moment about number 4, where it's asking, are there any rules, or sorry, are there any values of n where your rule does not apply? Alright, is there any reason that we could have a value of n for which this expression or this rule would not work out? Think about it for a second. And hopefully you've come to this conclusion. That rule will not work if n is equal to -1. So we're going to say n cannot equal -1. And quite simply, the reason for that is that if n was equal to -1, when you multiplied right here by 1 over n plus 1, you'd be multiplying by an undefined expression. Okay, so that rule works as long as the exponent for your original power function is not a -1. Alright, let's formalize this a little bit more. And talk about what's called a power rule for antidifferentiation. Now, you know a power rule for differentiation, and that just means it tells you how to differentiate a power function. And now we're learning how to write the antiderivative of a power function. And if you remember, a power function is just anything that can be written in the form x to the nth power, where you could write x to the 1/2 power, or x to the -3rd power, or x to the 17th power. And there's square root functions, reciprocal functions, lots of things that can be written that way. Okay, well, we just said that the antiderivative of such a function would be you increase the exponent by 1, multiply by the reciprocal, add a constant at the end. Alright, we need to put that into practice with a few different functions. We're going to show you how to find the antiderivatives of these functions that you see on the screen right now. I'm going to do the first couple with you, at least, and then let you try the remaining ones. Watch this. If I want to find the antiderivative of x to the 11th power, I'm going to increase its exponent by 1, I'm going to multiply by the reciprocal, and I'm going to add a constant at the end. And I can do the same with all the other ones, provided that I have them written in that form x to the nth power to begin. For instance, part B, I could write that as x to the negative fifth power, and then apply the same rule. Increase the exponent by 1, multiply by the reciprocal of that exponent, and then add c at the end. I can write the eighth root of x to the fifth as x to the 5/8 power. And then the antiderivative, well, increase 5/8 by 1, you get 13/8. The reciprocal of 13/8 is 8/13, that's what our coefficient would become. And then you put your plus c at the end. All right? Go ahead and find the antiderivative of part D for me, please. And let's see how you did. You started off by rewriting the function as x to the negative 5/2 power. Then you increased negative 5/2 by 1 and got negative 3/2, multiplied by the reciprocal of that exponent, and then added a constant at the end. If you've got that, then you understand the most basic rule, power rule, for antidifferentiation. Thanks for listening. I'll see you next time.